Now we're going to be talking about logarithmic functions, which are basically the inverses of exponential functions, a number to the power of a variable. Why logarithms come about is we ask ourselves, how do we solve exponential functions that don't have the same base? How are you supposed to solve those problems? And this is when we use logarithms. So the definition of a logarithm, so if a is greater than 0, not equal to 1, and if our x is equal to 0, say we're given something where we have a to the power of y, so y is a variable, is equal to x. That is the same as writing this as a logarithm. So log a, and we say log base a, x is equal to y. So this thing right here, this is our base. And this is known as a log function or logarithmic function. I'm just going to start writing log, but logarithmic. That's the full term. Head seems a little bit bigger today. Okay, so let's do a few examples where we can go back and forth between the forms because it takes a little bit of getting used to. Okay, so let's say that we have these exponential forms. We're going to change them into log forms. So for the first one, 2 to the power of 4. So the exponent is the part that goes on its own side. So we have 4 log. This number here is the base. So this would be log base 2. And then whatever it's equal to on this side, the right-hand side. So this is going to be log base 2 of 16. This form and this form, these are equivalent. They mean the same things. It's almost like looking at the exponents and radicals. They're equivalent notations. How would I write 3 to the power of 2 is equal to 9 in logarithmic form? 2 here, log base 3 is equal, or sorry, log base 3, 9. Perfect. Now the next one looks a little bit weird. Okay, so we have the exponent. The exponent's allowed to be negative. So I'm going to have my negative 2 here, and then we're going to have log, so base 1 over 5, and then we have to the 25. Okay, what about the next one? So we have our exponent. The exponent, it's okay if that's negative, so I have negative 4. Log, the base of the exponent is 2, and then I have 1 over 16. For this last one here, this is a little bit of a special one. So log base e to 1, and as we're going to see soon, if you have log base e, we use a different notation. This is sometimes called ln, and we'll write this down formally in a second. So in terms of notation, they write it ln, but it's pronounced ln, and it's just a fast way of writing this. But when you have ln to the 1, this is always to 0. So let's do a few examples. The actual question didn't have the x here. I'm writing this down myself. I'm saying that whatever that number is, I don't know, but I'm saying that it's going to be equal to some x. And what do we want to solve? We want this value x such that I take the base is 4 to the power of x, and then whatever that is, I want it to be equal to 64. So my bases as of right now, this and this, these are not the same. My 4 to the x is equal to 64, but maybe I can write 64 in terms of 4. So if I did 4 times 2, 4 squared, that's going to be 16. If I multiply by 4 again, then I will get 64. Okay, so 4, 3 is equal to 64. And how did I know that? I don't actually have a calculator in front of me, but I tried it. I tried 4 squared. Oh, that didn't work. 4 cubed. Oh, okay, that's all right. And if I now make that change, write the right-hand side as 4 to the 3, now my bases are the same. And I can solve directly for my x. Okay, so what do we want? So again, we want an x such that, so my base is 2, to the x is equal to negative 8. There is a bit of a problem here. So this is what we want, but 2 to the x is greater than 0, okay, for all positive values of x. Positive values of x. This is an example of a log that's not defined. And if you saw this question, you wouldn't have to go through all of this to explain it. You can just say the log of a negative number is not defined. Okay, but that's the reasoning why. So we're just going to write out the formal definition of a logarithmic function. Okay, so the classification of this type of function. Okay, and then again, it's basically the same. A is greater than 0, a is not equal to 1. Our x is greater than 0, but whenever you see a function that looks like log base a of x, this is what we call a logarithmic function. And now what we were saying before was if the base of the logarithmic function is e, we refer to this as the natural log, or pronounced as ln. So the natural log, and denote it as follows. We denote it like this. So log base e of x is equal to ln, and I'm going to put here, pronounce it as like your lawn in your front yard. And whenever you see this, in terms of if you want to go back and forth to this in exponential form, log x equal y is the same as e to the y is equal to x. So if you ever see an expression e ln of x, you can just say they basically cancel each other and give you an x, similarly with e to the power of ln x. Okay, so these are really good things to memorize right here. And I said that the relationship between these were logs are the inverses of exponential functions, and they're mirror images about y is equal to x. So what does that mean exactly? It means that if I just draw this line, y is equal to x, so this is a line with slope 1, and the y-intercept is just 0. And if I were to draw e to the x, I would just, if I had a mirror, I would put it here, and then log is that mirror image. Okay, so this is just showing you the relationship between these two functions. So let x and y be any positive real numbers, r can be any real number, and let a be positive real number but not equal to 1. Okay, so that's just formally introducing the variables. So if you ever see the base and the log of the number itself are the same, so log base a, this is just equal to 1. Okay, it's like it cancels each other out. If you see log base a of 1, this is always equal to 0. And let me jump back here for a second. If you look at this log function right here, if x is equal to 1, this is where we cross 0, but we never go past the y-axis here. This just shoots down to negative infinity. Okay, so that's a good one to remember. If we have a negative value, as we said, this does not work with our definition. This does not exist. And 0, same thing, also does not exist. Let's say we have two real numbers that are multiplied together. We can split them up and we can add them. Okay, so be careful. It's not this one times this one, it's these things added together. For division, again, it's like an exponent, right? You can go from exponent to log, they're related to each other. So if exponents are being multiplied, same base, you can add them. Okay, so for division, you can split them up and then subtract them. If you have log base a x to the r, okay, where r is a real number, you're allowed to bring this r out in front of the log. Okay, so you're allowed to write it like this. If you have 1 over x for the thing you want to find the log of, what you can do is you can just write it as x here, and then you put the negative out front. If you have a to the power of log base a x, the a and a here match, you can just write this as an x. This one here, number 10, has a special name. This is called the change of base rule. And when you're doing problems, a lot of the time we prefer to work with the natural log. So that's when you have log base e. It's nicer to write all of the same properties still hold. Mathematicians, we really kind of prefer that. So if you don't like the base that you're working in, you can always change it. You can always change it by saying you pick the base that you want, Okay, so let's say that I pick C, whatever C is, and then you take the bigger thing. The way that I remember it is the bigger thing here is on top, log base C x, and then the smaller thing here, the thing that's further down, that's the one that goes on the denominator. So log base C a. And then if I picked my C to be E, then I can just write this as ln x divided by ln a. So if you have log base to the 1 over a, and you want to find this for x, if you want to get rid of the 1 over, you can do that, but you have to put a negative out front. If you want to switch the x and the a, you can do that, but this is 1 over that. And then finally, if you have log base, where the base and the thing you're taking the logarithm of, if you can write them in terms of the same base, then they're equal to n over m. Just really quickly, I want to show you and give you some intuition on why these things are true, because if you better understand that, it'll be a little bit easier to remember them. Okay, the main ones that we use, just so you know, the main ones that we use are 1 is important, 2 is important, you know, this is part of the definition, they do not exist, but these three, number 5, number 6, number 7, are the main ones we use in addition to number 10. Okay, those are the most important ones, and they're all provable. Let's consider the property that's probably going to be used the most, the one of multiplication. Okay, so you have log base a, x times y. I want to show that it's equal to this. Well, how would I formally show that? So I know that my log base a x represents some number, and same thing with log base a y. So what I'm going to do for convenience to make this easier to write out is I'm going to rename them. I'm going to call the first one here m, and I'm going to call the second one here n. And then by definition of logarithms, what I can say is that a to the m, okay, so I'm going to write these logs here, the m and the n, they're equivalent to writing a to the power of m is equal to x, and a to the power of n is equal to y. So if I multiplied these two values together, if I multiplied x and y together, I'm basically multiplying a to the m times a to the n. These a's, they're the same base, okay? So by our exponent rules, I can rewrite this as a to the power of m plus n. If I have my expression here for log, remember I called these things m plus n, and I have log a x plus log a y. Now let's use some of these properties, the ones that we're going to use the most, to rewrite these expressions that you're given. Let's look at the first one. So I have log base a x plus log base a x minus 1. So these two things are being added. They have the same base, so I can write it as one log function. Log base a, and I'm going to do big brackets here. Sometimes people don't use brackets. I always do it just to make sure I don't get confused. But then I just take my x minus 1, multiply them together, and there we go. Now for this one I'm going to split it up. I have division here. So I have log base a, and then I have this expression divided by this expression. So I can subtract them. Log base a, x squared minus 4x. And then it's being divided, so I have minus log base a, x plus 6 here. So if I gave you this one, you can write it like this because they have the same base. Let's use some of the other properties just to get a little bit more practice. I can factor out an x. I can go log base a, and again, I'm going to put big brackets here. I can factor out an x, so I'm left with an x minus 4. And then the second one here, I leave it alone. Okay, there's nothing I can do with this one. But now I'm having multiplication. You can split this up into two separate terms where you add them. Okay, so we can go log base a to the x plus log base a to the x minus 4. And this last one here, I cannot change it, okay, because the thing inside the log is being added. You can't change it for addition. All right, let's do another one with another popular rule. So now we have log base a, 9x to the 5. We're seeing an exponent here, so the tempting thing to do is to maybe bring down the 5 right away. But remember what that 5 is actually being applied to. The 5 is the exponent for the x, and the 9 is being multiplied by that. So really what this means, and again, this is why brackets are super helpful, this is equivalent to saying log base a 9 times x to the 5. So before I can bring down that exponent, I first have to split it up. I have to split it up into log base a 9, and now I'll have a second term, log base a x to the 5. And now for the second term, I can bring down the 5. Okay, if there was a bracket here and here, so the 5 could be distributed to both of them, then you could bring the 5 directly down. But otherwise, you have to split it up like this first. So log base a 9 plus 5 log a to the x. And just a couple of remarks, what I call common logs. Log base 10, this is used a lot in music, which is just abbreviated log x. So for log base 10, they don't normally write the base. Okay, and then for log e, which we said before, that's the natural log, which is pronounced ln of x. And I kind of showed it before, but again, what does it look like? If x is equal to 1, we cross, and then, it looks something like this. It grows much slower than exponential functions. And then between 0 and 1, so between here and here, the value just gets more and more negative. And then this was the thing I said about the change of base formula, that if I want to change the base, I can change it, say, to some value b, where I have log base bx divided by log base ba. And if I write b as e, I can instead just write my expression as log base ax, and log base c, I can just change those to be lns. Okay, now we're going to solve each of the following equations. Okay, so by definition of logs, if I want to change it to exponential form, what is my base of the log? It is an x. So x cubed is equal to, the thing I'm taking the log of is 8 over 27. Now I'm trying to solve for x here, okay? So this also reviews a bit of what we were doing last week with radicals and exponents. Taking everything to the power of 1 over 3. If I do that, then I have my x by itself, and then I have 8 over 27 to the power of 1 over 3. So by exponent rules, this 1/3 is being applied to both the top and the bottom. Okay, so we can write this as 8 to the 1/3 divided by 27 to the 1/3. And I know that that's equal to 2 over 3. So let's first convert this expression here. So log base 4x is equal to 5 over 2. Let's now change this to exponential form by the definition. So what is our base? Our base of this log is 4. Okay, we have that the log expression is equal to 5 over 2. And this is equal to my x here. So if we simplify it a little bit, let's try to get rid of these exponents. This means 4 to the half, 5. Or you can write it as 4 to the power 5 all times 1/2. But we know what the square root of 4 is. The square root of 4 is equal to 2. Okay, so I can write this as 2 to the power of 5. And what is that equal to? That's equal to 32. This one we have logs, but they still have the same base. Okay, so we can use our properties. We're going to have log base 2 x divided by x minus 1, and this whole thing is equal to 1. Okay, so now we're in a position where I can switch it to exponential form using the definition. So what is the base that I'm working with here? I'm working with a base of 2. Okay, all of the log stuff is equal to 1. And then I have x divided by x minus 1. And I want to solve for my x value. So I'm going to bring this thing up here with the 2. So I have x is equal to 2 times x minus 1. Okay, so I have x, 2x minus 2. I can bring all of my x's over to one side, to the left side, and I can magically do it like this. Okay, so x minus 2x is equal to negative x, negative 2. The negatives cancel each other out. The reason why logs are also really important, so think about COVID-19, for example, the pandemic. The rate at which it's spreading is exponential. We're eventually going to do this problem, and we're going to look at the growth of COVID-19 and how it's infecting people. But when you're looking at exponential functions, it's difficult to look at the graphs because of how quickly they grow. So using logs is a really nice way to smooth them out, because logs, when you graph them, they look something like this. Okay, but they're inverses of exponential functions, which look like this. The one that I just drew is much harder to read information with compared to a log. So sometimes what people do is they'll take an exponential problem, and then they'll take the log of all the x values, the log of all the y values, and then they'll replot it so they can more easily see what's happening. Okay, so base 10, I don't want to write the 10. You can if you want to. Okay, if you're concerned that you're going to get confused, throw the 10 in there. But they're being added, so I can write log, and then have x times x minus 3, and then I have that this is equal to 1. Okay, so now I'm going to convert it. Okay, so I am going to put this here just for people reviewing. I know some people don't have as much experience with logs. So I have my base is 10, so I have 10 to the power of 1 is equal to the stuff in the inside. Okay, all right, this is nice. Now, when I expand this, so what gives me 10? 5 and 2 is a candidate. And because this is minus, one of the terms will be minus something, one of the terms will be plus something. Okay, we have negative 3. So if I have negative 5 plus 2, then it's going to be okay. Remember, this means that this term is equal to 0. This term is equal to 0. So if you have x minus 5 is equal to 0, you still have to isolate for the x. Negative 2. Okay, perfect. So now I have 5, and now I have negative 2, but I still have to be careful here. We can't have the negative 2, cannot have x's that are less than 0 or negative. So x is equal to 5 is the solution, okay? Be really careful about this. Okay, let's do a few more now in the other direction. 3 to the power of x is equal to 5. I can't change this 5 to somehow become a 3. It doesn't work. So we say the bases are different. When you come across different bases like this is when you use logarithms. Okay, so we're going to use a log. And because you're allowed to choose whatever log you want, whatever base you want, I personally prefer the natural log, okay? The one where it's log e, because then I can write ln, and I'm an efficient mathematician, so writing less is good for my hand. So what I can do is I can take ln 3 to the x ln 5. Okay, and remember, I'll write over here, ln of something is just when you have log e. Okay, and because I don't say use a specific base, use whatever you want. I can bring this x down out front here. I have x ln 3, and then I have ln 5. Now remember, ln 5 and ln 3, these are actual numbers, okay? So I would highly recommend not putting these into your calculator because these are irrational numbers. What does that mean? It has infinitely many decimal places. I highly recommend that you leave it like ln 5 divided by ln 3. And if you want to know roughly what it's equal to, just so you can calibrate in your head on how big it is, this is roughly 1.465. Let's try this one now. So again, we're having different bases here. So this is why we think to use a log. And again, I'm personally going to use ln just because I like it. So I have 3 to the power of 2x is equal to 4 to the power of x plus 1. And I think about this like taking the ln of my left-hand side and my right-hand side. I'm going to have ln of each side, so ln 3 to the 2x. And then I have ln 4 to the power of x plus 1. Okay, so I have 2x ln 3. And now that ln 3, that's just a number. Okay, and then just be careful with your brackets for the right-hand side. This is x plus 1 all multiplied by ln 4. Okay, and again, this is a number. So now we have to be a little bit careful because I need to expand my right-hand side because I want to bring all my x's on one side. So I have 2x ln 3. My right-hand side, I have now two terms. I have x ln 4 plus ln 4. I'm going to leave my ln 4 on the right side, and then I'm going to have 2x ln 3 minus x ln 4. And again, don't let these lns trip you out. Okay, this here is just a number. And then my ln 3 and 2 is just a number. So what I'm actually going to do to make it a little bit easier to see how you factor the x is I'm going to write it like that. So I have an x in both terms, so I'm going to factor it out. 2 ln 3 minus ln 4. Sorry, I'm going to move my minus sign because my writing is getting messier. Ln 4 is equal to ln 4. And now I just have to divide. So I isolate for my x, and I do so by dividing ln 4 by this big number in brackets that looks absolutely beautiful. And that is sarcasm. All right. Now let's do this one. And I know you're thinking, this looks a little bit gross. Why are we doing this? Because in health sciences, these are the types of numbers you see. Okay? So I don't want them to freak you out at all. So now we're going to have 5. Now we're working with our e here. Okay, that 2.7 blah, blah, blah. To the power of 0.01x is equal to 9. If we did take a ln of both sides, as of right now, right, so if I went ln of this stuff, I would have these two terms that are being multiplied. I can split this up, but to save a few steps, something I can do because ln and e cancel is I can rearrange this a tiny bit before I take the ln. I can divide by 5. And why do I want to do that? I want to do that because now if I take the ln, my left-hand side is going to simplify very, very quickly. Okay, my ln and my e, remember, these things cancel each other out. I can jump, if I wanted to, straight to this step, where I just have 0.01x, ln of 9 over 5, this is just a number, okay, so we're going to leave it. We can bring down the exponent part, and then we have ln e. And if you even have a calculator, type in ln e, it's going to give you 1. Okay? And now I'm almost done. I have one more thing. I have to just divide by the 0.01 to isolate for my x. And I have that fabulous number right there. Okay, so the change of base theorem for exponential. So we wrote down the change of base theorem if you want to change the base for a logarithm. But the one if you want to do it for instead the exponential form. So if you have a to the x. Okay, and this will be useful when we start doing derivatives. We're going to see this rule more then. But if you want to get e's and lns involved here, this is the same as writing e to the power of x ln a. Okay, now why is that exactly? So, again, proofs, you don't need to know proofs, but I want to show you why it's true so it doesn't seem more mysterious and you can remember it. So because your e's and your lns cancel, right? If I have e to the ln a, that's equivalent to just write down a. They cancel each other out. So if you start with this, which is something that you're more familiar with, so this e ln a, that's equivalent to just a. And then I take all of this to the power of x. Then I get that rule. That e ln a, because that x is in the exponent, you can write it out front, and then you have a to the x. If I have 7 to the power of x, I think about going e ln to whatever it is the thing I want to change. Okay, so we have 7x, we take the e and the ln of it, and then e x ln 7, and then that's our expression. So that's typically how this is used. Okay, so let's say we want to approximate this exponential function as an a to the x. I just want to see exactly what my number is and what my variable is. So e to the 2x, we can split this up by our exponent rules as e to the 2, and then all of that to the x. Okay, so this right here would be considered our a. Okay, so this is just showing you manipulations that if you want to do the change of base for logs, or if you want to do them with exponents. Doubling time. So this is when we're starting to see the cool things about logs and e's. So if a population of squirrels, okay, grows 5% per year, how long will it take for the population to double? So when you hear about all these problems on the news about, the population growth of humanity is at this point, by 2050, we're going to reach 12 billion or whatever the heck it is. How are these were people coming up with these numbers? So it's doing problems like this. So doubling time is a simplified version of it. So let's say our population doubles after t years. Okay, I don't know what t is, but t years, it happens. And an annual growth rate of 5% per year. Then t is given by the equation. Okay, so 1.05 to the t. The 2 comes from, I want my population to double. I want to double. This is talking about, a current population is 1, and then I want it to increase annually by 5%. 5% in terms of decimals, my favorite thing, 0.05. Now I want to solve for t. Okay, these are different bases, so I'm going to take this to the ln. So ln of 2 is equal to ln of 1.05 t. And now what can I do with that t? Because it's within inside the ln, I'm allowed to bring it out. I'm allowed to bring it out front here. Okay, so the ln 2, this is just a number. And then I have t ln of 1.05. And now I just have to isolate for my t. So ln 2 divided by ln of 1.05. Okay, so if you plug this into the calculator, you're going to get 14.2 blah, 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 blah. So what does this actually mean, the punchline of this question? It will take a little over 14 years for this squirrel population to double. Okay, and this problem, don't worry about this too much right now. Okay, but this problem, it can be generalized for a growth equation. In our situation, we had y naught is equal to 1. And for us, we were interested in the population doubling. If we wanted it to triple, we would put a 3 here instead. Okay, and depending on the current state of our population, this number would be different. Don't worry about that right now. But just so you see what it looks like in general, here it is. And if you've done interest problems, you probably also have, this is the initial amount of money you have. This is the amount of money you'll have to pay over t amount of years with an interest rate of whatever.